Hello. So, recollect that the last lecture we had shown that the complexity of computing reciprocal of a number of n bit was of the order of multiplication of two n bit numbers. This is what we had shown last time. Our long term goal is to show that with say some C1, which this result shows, we also would like to show that this in turn for some C2 is less than equal to square operation. So, squaring a number of n bits that is bounded by the reciprocal. We will also try to show for some C3 is that multiplication itself is bounded by square operation time, and therefore all these three operations are within a constant from each other. It is not our objective to give an algorithm for these, but just to compare the complexity. All the basic operations of integers, that is to say multiplication, reciprocal and square, are within a constant time from each other, and notice that these are equivalent with respect to some other coefficient of division, that is to say a reciprocal and division, they are also within a constant time from each other, and that is trivial because you can perform division by computing reciprocal and then multiplying by the numerator, and the reciprocal is a special case of division. So, today what I am going to show is this inequality. I will try to show that we can bind the time of square by the reciprocal. Now, the basis of our today's discussion is the following observation, namely that p square is 1 over p minus 1 over p plus 1 minus p, because if you simplify this, you are going to get p times p plus 1 over 1 and minus p, which is simply p square minus plus p minus p, which is simply p square. Hence, what we will try to do is that we will try to construct the square of a number, n bit number, by computing actually three reciprocals. There is 1 over p plus 1 and 1 over the difference of the two. This is the goal. Now, notice that when we deal with actual numbers of certain size, we will have to adjust certain things. So, things will be slightly different from what appears here, because we do not have exact numbers such as 1 over p or 1 over p plus 1. We can only approximate them with certain accuracy. Now, I am going to write down the algorithm first, and then which is really motivated by this observation, and then we will try to show the correctness of it. Now, there is one small fact about p. P we are assuming is an n bit number. So, p itself is actually within 2 power n minus 1 and 2 power n minus 1. But if we have p equal to 2 power n minus 1, then p plus 1 will become less than equal to 2 power n and strictly greater than 2 power n minus 1. The difficulty on this side is that if it becomes equal to 2 power n, then it becomes an n plus 1 bit number, which causes certain difficulty. So, this one lone case when p is to the power n minus 1, we can handle that separately, and then we will assume that p is strictly less than this, which will make this strictly less than 2 power n. Then both these numbers will remain n bit numbers. So, our algorithm, I'll go square, takes p to be an n-bit number p1 through pn as input, and if p is equal to the power n minus 1, then return, we know directly the square of this number, which does not require much effort. We will return to the power n plus to the power n plus 1 plus 1. Oh, sorry, minus this plus 1. So, this one case we have separately handled. Else, we will first compute I, which is reciprocal of 2 to the power 2n times p. Notice that instead of taking an n-bit number, we make it a 3n-bit number, because we need quite a bit of accuracy in our numbers. And similarly, I will compute j, which is reciprocal. This is the same algorithm that we have discussed in the last lecture, 2 power 2n times p plus 1. Then c is I minus j. Then if then we are computing d. D is reciprocal of c, and now here one special situation arises, which we will understand later on. That is, if c is a 2n plus 1 bit number, then define d to be d by 4 will replace by d will be replaced by d by 4. Now, effectively d is this number. I mean, barring of course whatever happens due to the boosting of the bits into the number. If we adjust those things, d will be about this number, and a will be our approximation for p square, this minus p, that gives us a. Unfortunately, a may not be exactly p square. There is no room for approximation for p square, because it is an integer and p square exists within the representation range. So, what we will have to do is make some corrections. Later on we will show what corrections are to be made, but here we are going to leave some remark, make some correction, and then return the value. That should be the value of p square. So, now let us go about analyzing this algorithm. Now, as I mentioned, we will assume that our p and p plus 1 are both n-bit numbers. We will stay with that, because this case has been separately tackled. Now, if you recollect from the last lecture, p times 2 power 2n times p times I is less than equal to 2 to the power, notice it is a 3n bit number. So, we can do that as 6n minus 1. This is what we expect that the reciprocal should give me, and should be strictly less than 2 power 2n p I plus 1. This is from the what guarantee we get from the reciprocal. Okay. By the same token, 2 power 2n p plus 1 times j is 2 power 6n minus 1, which is less than 2 power 2n p plus 1 j plus 1. These are from the fact that I and j are computed as reciprocal of these numbers. I can simplify them. So these are going to simplify to p times I less than equal to 2 power 4n minus 1 less than p times I plus 1. Just cancel out 2 power n, and also from here. So you are going to get p plus 1 times j less than equal to 2 power 4n minus 1 less than p plus 1 j plus 1. We get these. Now, let's try to find a bound for I from this. So I am going to write down a bound for I as I is less than 2 to the power 4 minus 1 power 4n minus 1 over p and here we have I plus 1, j is 2 power 4n minus 1 by p plus 1 less than j plus 1. Now, our C, which is I minus j, we can now bind from above and below in terms of these terms. So, let us see what does that give us. Minus j minus 1 is less than minus of this. So, I less than 2 power 4n minus 1 by p and minus j minus 1 is less than 2 power 4n minus 1 by p plus 1. Combine these two and you get I minus j, which is C minus 1 less than this is minus, this is minus, this minus this, which is 2 to the power 4n minus 1 into 1 over p minus 1 over p plus 1, which is nothing but p into p plus 1. Now, if I use the other inequalities, I will get 2 to the power 4n minus 1 by p is less than I plus 1 and minus 2 power 4n minus 1 over p plus 1 is less than minus j. Again, if I add the two, I am getting C plus 1 to be less than 2 power 4n minus 1 over p into p plus 1. We get a bound above and below for C. Combining the two, we have our first inequality C is less than 2 to the power 4n minus 1 by p square plus p plus 1, and the other inequality is less than 2 to the power 4n minus 1 over p square plus p minus 1. We have these two bounds. Let us say this is, I am going to call this equation 1. Okay. Now, if I multiply the whole thing by p square plus p over c and simplify this, this thing turns out to be 2 to the power, let us just write down here, 2 to the power 4n minus 1 over c minus p square plus p by c less than, notice I am multiplying by p square plus p divided by c in the entire thing. So, this becomes p square plus p. Over here this becomes 2 power 4n minus 1 over c plus p square plus p by c. So, we get 2 power 4n minus 1 by c minus p square plus p mod is less than p square plus p over c, and this is my equation number 2. Okay, so let me just rewrite the inequality that we had, which is 2 power 4n minus 1 over p square plus p. I think we made a mistake. We should have had less than or equal to here, c not strictly less. It's 2 power 4n minus 1 over p square plus p plus 1. This was our first equation, and the second one we had was mod of 2 power 4n minus 1 over c minus p square plus p is less than or equal to p square plus p over c. Now, we know that the range of p itself is in the range 2 power n minus 1 and 2 power n minus 1. So, p square plus p, that is p into p plus 1, that will become 2 power n times 2 power n minus 1 here, and over here we will have 2 power n minus 1 into 2 power n minus 1 plus 1. Okay. So, that gives me an lower and upper bound for p square plus p. I am going to plug this in and get yet another bound for c. So, from 1, what I find is that c on this side is 2 power 4n minus 1, and I am going to plug in the larger of the two values, that is 2 power 2n minus 2 power n minus 1. Over here 2 power 4n minus 1 by 2 power 2n minus 2 plus 2 power n minus 1 and plus 1. This can be simplified slightly, 2 power 3n minus 1 by 2 power 2n minus 1 c 2 power 2, I am going to remove n minus 1, so it is 3n over 2 power n minus 1 plus 1 plus 1. Okay. Yes. To power this one. Yeah, we got rid of, oh, this is just 2 power, my mistake. This is just 2 power n minus 1. Yes. So, this is this minus 1, you are right. I would like to now estimate this number, and similarly this one. Okay. So, let us see what happens is, this is 2 power 3n minus 1 divided by 2 power n minus 1. I can take 2 power 2n here, I will get 2n minus 1 rather. Well, I got to clean it up. Let me retry. This is 2 power n minus 1 dividing 2 power 3n minus 1. This is going to be 2 power 2n minus 1 gives me 2 power 3n minus 1 minus 2 power 2n minus 1. I have 2 power 2n minus 1 left. So, that will be plus 2 power n minus 1 and something. We will just stop there. And on the other hand, the right hand side, we have 2 power 3n to be divided by 2 power n minus 1 plus 1. That means we have to take in the quotient 2n minus 2n plus 1. So, we have 2 power 3n plus 2 power 2n plus 1. We get minus 2 power 2n plus 1. So, I am going to have a minus 2 power n plus 2, n plus 2, and we will stop here again. So, maybe there is something more here, lower terms. So, this inequality becomes 2 to the power 2n minus 1 plus some epsilon. Notice that this one is not much comparable with what we have here. So, we can very much ignore the importance of this. We have a larger positive term there. So, we have some epsilon 1 c 2 power 2n plus 1 minus epsilon 2, negative term here, and once again because of that large negative term, a plus 1 does not really matter. What you notice here is this number, this is 1 followed by 2n minus 1 zeros and some small number. This will be a 2n bit number. So, 1 followed by 2n minus 1 zeros. So, this and plus something is not going to reduce the number of the size of the number. On the other hand, this alone is 1 followed by 2n plus 1 zeros, but the moment you subtract something, 1 bit goes down. So, this becomes only 2n plus 1 bit number. What we have here is two possibilities for C. Either C is a 2n bit number or 2n plus 1 bit number. These are the two possibilities we have to deal with separately. Okay. So, now we will have a in our program we are computing D, which is the reciprocal of C here. But depending on the size, the reciprocal will compute two different numbers. So, D will be 2 to the, if it is 2n bit number, it is going to give me 2 to the power 4n minus 1 over C minus some small fraction here. Say we have epsilon 3 here. If C is a 2n bit number, and over here, because it is a 2n plus 1 bit number, we will have 2 to the power 4n plus 1 by C minus epsilon 4 if it is 2n plus 1 bit. C is bit number. These are the two possibilities. Now, therefore, what our algorithm does is that in this case we divide D by 4. So, in the step if you recollect, the algorithm had a step here which said if C is a 2n bit number, 2n plus 1 bit number, then we computed D to be D divided by 4 floor. We have done this. So, this was the step number. So, after this step, let resulting D be D prime. Let us suppose D prime denotes the number that we compute after this step. So, D prime will remain this if C is a 2n bit number, and D prime will become this divided by 4 if it is a 2n plus 1 bit number. So, what we notice here is that D prime minus 2 to the power 4n minus 1 over C is less than 1. Notice that this is less than 1. Our error is within 1. Okay. So, I will label this equation as equation number 3. So, we have 3 crucial equations that we want to use, 1, 2 and that one 3. Okay. So, from 2 and 3, let us take a look at these two equations carefully. One of the terms is same in both. Now, imagine you have a real line. Over here we have the term 2 power 4n minus 1 divided by C. Then D prime is within, this is plus 1 and minus 1 from this reference. This is where my D prime falls, somewhere here D prime falls, and within plus minus p square plus p by C. So, over here you have plus p square plus p by C and minus p square plus p by C. In this range occurs p square plus p. Okay. So, because this is the difference between these two bounded by p square plus p by C within this range. Hence, the difference between D prime and p square plus p, D prime is in here, p square plus p is somewhere here. So, the difference between D prime and p square plus p must be at most p square plus p by c plus 1, okay, in absolute sense. So let us try to state that we have from 2 and 3 the difference between d prime and p square plus p is less than p square plus p by c plus 1. That is the most that is possible between these two. So now we have this inequality. For c I need a lower bound. We had a lower bound here, which is to the power 2n minus 1 plus something. So we can say that this difference d prime minus p square plus p is bounded above by p, of course, is to power n minus 1. So this becomes to the power 2n minus 2 power n, that is the upper bound for p square plus p, divided by a lower bound for c is 2 power 2n minus 1, 2 power 2n minus 1, and then overall we have a plus 1. This quantity is, of course, less than 3, because this leaves only 2 minus something plus 1. So we have overall difference between what we have computed and what we want to compute is at most 3. So now let us just go back, recollect our algorithm, which I will rewrite again. Algo says if p is 2 power n minus 1, then return 2 power 2n minus 2 power n plus 1 plus 1, else we had I reciprocal of 2 power 2n times p, j was reciprocal of 2 power 2n into p plus 1, c is I minus j, d is reciprocal of c. If c is 2n plus 1 bit number, then replace d by d divided by 4, and then we say a is given by d minus p. At this point what we have noticed, notice that d is what we had pointed out as d prime here. A is d prime minus p. So this is pointing out that the difference between a and p square is at most 3. So at this point we would like to correct a, because the error might be of up to 3. But how do we do that? The problem is, it is p square that we want to compare a with. We can't compute p square, because all we are allowed to do is compute reciprocal. So there is a nice trick we can apply. What we will do is that if you look at a is in terms of bits, what we have here is that if I cut off a up to some point, In other words, if I compute A modulo 16 and I compute say P square modulo 16, if I compute these two numbers, if they are equal, then their modulo will be equal, of course. But in case they are off, then they are at most off by 4, maybe 3. So what will happen is that here the difference between these two numbers, let's say this is A prime and this is say B prime, then the difference A prime minus B prime is also the difference between A and P square, because we know that the difference does not exceed 3. See, the only information we lose if the difference was a multiple of 16. But if this is my 0, and if I compute 1, 2 and so on and 15 in this cycle, our error can be positive or negative, of course. So if somewhere here, this is where A modulo 16 is pointing in this clock, then up to 3 points here or up to 3 points here will be the place for P square mod 16, okay, up to 3 here and up to 3 here, because it's plus or minus, we do not know. But that will be visible in modulo as well. We will not lose, because this cycle is of 16 size. Hence, it is good enough to compare A mod 16 and P square mod 16. And whatever error comes, that we can add or subtract to A to get exactly the value of P square. So what we are going to do is compute x to be A A mod 16 minus P modulo 16 square mod 16 and the whole thing modulo 16. And then we are going to give A to be A minus x. This is exact error between A and P square, as we have argued. Hence we have, so A minus P square we have adjusted. So at this stage we can now return A. This must be exact value of P square. So now it's time to estimate the time complexity of this algorithm. In this, we have computed reciprocal of two 3n-bit numbers. These are both 3n-bit numbers. So our time to, or rather I'll just use Sn. Sn is the time to square is less than 2 times reciprocal of 3n plus C is a 2n bit or 2n plus 1 bit. So it's R 2n plus some linear terms, because we are subtracting, so over here as well as here. So this is what is an upper bound for our whole process. reciprocal we have already shown is as hard as multiplication, which is at most square, quadratic. So this can be less than of Rn is 18 of Rn, and this is at most 4 of Rn. So the whole thing is 22 of Rn plus some Cn. Notice that I have used the fact that R of An is less than A square of Rn. And this is of course linear, so this whole thing can be written as 22 plus C Rn. So this was one of the objectives in this series of inequalities that we wanted to establish, that Sn is bounded linearly by Rn. So far what we have accomplished is S of n is less than equal to some C1 of Rn, which is less than equal to some C2 of Mn. These three things are done. Now a very simple argument can show that this is bounded by Sn. So let us try to show that M of n is less than equal to some C3 of Sn. Suppose you have, say, suppose A and B are n-bit numbers. So let us take some C equal to A plus B, which can be up to n plus 1 bit in size, up to n plus 1 bits in size. Now if I square this, so C square is A square plus B square plus 2AB so this product AB is nothing but C square minus A square minus B square over 2. So I can compute the product of two n-bit numbers by squaring an n plus 1 bit number and two n-bit numbers. So what we have shown here is that Mn is less than equal to S of n plus 1 plus 2 of S of n plus some C prime times n. Now this C, which is say n, if it is an n-bit number, then there is no problem, this will also be Sn. If it is an n plus 1 bit number, then it will look like 1 plus an n-bit number. To square this, this will be 2 to the power n, this will be 2 to the, so I will write down this as some alpha to the power n plus a C prime, which is an n-bit number, and alpha is 0 or 1. So C square is nothing but alpha square, which is again 0 or 1, 2 to the power 2n plus C prime square plus alpha times 2 to the power n plus 1 C prime. This involves only one squaring of n-bit number, and others are linear operations. Hence this can be reduced to some 3 Sn plus some C double prime n. Which can again be, notice that Sn is more than linear. So this I can write down as 3 plus C prime, C double prime S of n. Hence, we again have some C3 and so what this whole cycle says that the difficulty of all these three operations are equal. They are within a constant factor from each other. And the last thing that I had mentioned at the start also is that if dn is division of an n bit number by another n bit number, this can be estimated by first compute a and then multiply it to a reciprocal, which is to the power some 2n minus 1 by b, multiply these two and then adjust your bits, the decimal point, to get a by b. So, this involves one reciprocation and one multiplication. Hence, the difficulty of division is also of the same order as these. Hence, all the basic integer operations on an n bit number are of equal difficulty. This is the objective of our discussion and this is what we have established. In the next lecture, we are going to show the similar kind of relation exists on polynomials on single variable, because the ideas are very similar and we will be able to show the similar kind of relation.